In this video, we're going to talk about paths and velocity. We're going to go through this overview slide first, and then we'll go back through each topic and cover each one in more detail and with more examples. This is one of those topics that seems to sort of just be, just kind of inserted in, and then afterwards the next few topics have nothing to do with paths and velocity, but I'm going to warn you now that you'll see this again by the time chapter 6 or 7 comes up, when you talk about integrals along path integrals for vector fields, for scalar. It's just all over the place in chapter 7, I believe. And so one, I'm going to tell you, you will definitely see this again. And not only will you see this, this will be the starting point. So you want to be solid on this so you can build on top of that. The second thing I'm going to say, it's really useful in physics and engineering because this is like when you're integrating along a path or you're summing things up along a path, like maybe a force or something. And then the other thing, if you're not in physics or engineering, it's still really important if you're a math major because you will see this all over the place once you do complex analysis, when you start integrating in complex. So that's the end of that diatribe, and we can start with the definition of a path. A path in Rn is a map from the interval a to b, so along the real line a to b, and then it gives you something in Rn, an n-dimensional space. So if our path sigma is differentiable, we say sigma is a differential path. The points sigma a and sigma b, again, this is the endpoints of our path because a and b are the endpoints of our line on the real number line. The image of sigma is called the curve of sigma. It is useful to write t for the variable, so this would be sigma of t, and we think of sigma of t as tracing out a curve in Rn in 3 space as t varies, or n space as t varies. Often we think of t as time, and sigma of t to be the position of the moving particle at time t, and we can write sigma of t is equal to, if we're in 3 space, x of t, y of t, and z of t. So again, t is time, and then this function sigma will give us the position at time t. So examples are the line through a point x naught, y naught, z naught with direction in the direction of the vector v is the curve of the path sigma of t equals x naught, y naught, z naught plus t and then your direction vector v. This is the formula we learned from chapter, like probably the first video we did, chapter 1.1. The unit circle in the plane is represented by the path. Sigma of t is equal to cosine of t, sine of t, and this one you'll become really familiar with, or you should, but we'll do examples of this one as well. And the path sigma of t equals t squared. In this case, our x-coordinate is equal to t, and our y-coordinate is equal to t squared. So in other words, our y-coordinate is equal to x squared. So this is a parabola, and the curve is the graph of f of x equals x squared. Again, we have y. Our y-coordinate is equal to the x-coordinate squared. And so we have this graph here of the parabola. Once we think of sigma as a position, then the velocity vector is given by v of t, which is equal to sigma prime of t, which is just the derivative of the components. So if we're in 2 space, that would be x prime of t, y prime of t. The speed of the particle is given by s of t, which is the magnitude of sigma of t. That is, the speed equals the length of the vector sigma prime of t. Next, we have the tangent line. So if sigma is a C1 curve in R3, the tangent line of sigma at sigma of t is given in parametric form by L of t, that's the line, L of lambda is equal to sigma of t naught plus sigma lambda sigma prime of t naught. For example, if sigma is our path, t is time, and it gets mapped to cosine t, sine t, and t in 3 space, then the velocity vector is sigma prime of t. Taking the derivative of cosine, we get minus sine of t for x. Taking the derivative of sine, we get cosine t for y. And taking the derivative of t, we get 1 for z. So the speed at a point is the magnitude of the velocity. So speed and then is the magnitude of our velocity vector. So that's going to be sine squared of t plus cosine squared of t plus 1 square rooted, which is equal to the square root of 2. And note the point moves at a constant speed, although its velocity is not constant, and it's not constant since it is continuously changing directions. And here's the graph of this path, by the way. It's the sine cosine, which gives a circle, as we mentioned up here, but this, actually here's the path. The sine and cosine give us the circle, but this t here means the circle is continuously moving up. So it's kind of this kind of a helix over here. And as we see, it's continuously changing direction, so velocity is not constant. A second example, consider a particle moving on a path described in this previous example. So here's our sigma of t, where t is time. At time t equals pi, the particle leaves the path and flies off on a tangent. Find the location of the particle at time t equals 2 pi. Assume no forces act on it after it leaves the helix. At time t equals pi, then, we can figure out its position right as it flies off, or right before it flies off. So sigma of pi is going to be cosine of pi, sine of pi, and then pi, which is equal to -1, 0, pi. When we take the derivative of sigma, we're going to get minus sine of t, cosine t, and 1. So we plug in sigma prime of, this should be pi, that's going to be 0, -1, 1. And this is the direction of travel right as it flies off. Now we have enough information to write the equation of the tangent line. We need theta of t naught plus some constant lambda prime of t naught. So our t naught, so right as it flies off, is pi. So we have our theta of t naught, so that's -1, 0, pi, plus our constant t times the velocity, which is 0, -1, 1. At time t equals 2 pi, that's pi time units since flying off on a tangent, so we can plug in pi here and we get -1 minus pi 2. This here then is our position at time t equals 2 pi, pi units after it flies off on a tangent. That completes our overview. Now we'll go through each topic in more depth and with more examples. We start with the definition of a path in Rn, which is a map from an interval of real numbers to Rn. So for example, if sigma of t is given by t squared, then sigma goes from some interval of real numbers, and I'm just going to consider the interval between -2 and 2, and it's going to map to R2 in this case because I have an x and a y coordinate. And the thing is, the points sigma of t, sigma of a, and sigma of b, in that case would be sigma of -2 and sigma of 2, are the endpoints of the path, and the image of sigma is called the curve. It's useful to write t for the variable as I have here, and think of sigma of t as tracing out a curve in Rn as t varies. We often think of t to be time, and sigma of t to be the position of a moving particle at time t. So if we look at this, so we're going to consider time between -2 and 2, and this will be the position that our particle is in at time t. So at time t equals -2, our particle is going to be at position -2 and then -2 squared, which is 4. So our position is -2, 4. So this is our position, and this is at time t equals -2. As we move through time, I can't do all the real numbers, but we'll just choose t equals -1. Our position now is going to be at -1 and -1 squared, which is just 1. So we're over here at t equals -1. At t equals 0, our position is going to be 0, 0. So I should write t equals 0. And then as t progresses to 1, our position is going to be over here at 1, 1. And then finally, when t ends at time t equals 2, our position is at 2, 4. So what we have is this particle is tracing out this path, this parabola shape, going this direction. And then I have labeled the different time points that I used. And again, this sigma of A, that would be our negative 2, 4, and sigma of B, that would be 2, 4. These are our two endpoints of the path. Just looking at this definition again, so our path goes from some set of real numbers to Rn. So if sigma is differentiable, we say that sigma is a differentiable path. So in other words, if we can take the derivative, sigma prime of t, in this case it would just be 1 and then 2t. We just take component by component, differentiable. Then the points sigma A and sigma B are the endpoints. The image of sigma is called the curve, so this is called the curve. And it's useful to write, we talked about this. And then finally, we can write sigma of t in terms of x of t, y of t, and z of t. In other words, in this case, when sigma of t equals t and t squared, so our x coordinate then is equal to t, and our y coordinate is equal to t squared. And this also kind of spells out the fact that y is equal to x squared, which is our familiar parabola. So often if your first variable is t, then you would consider this, you would be good to think of this as y equals and then whatever this x form is. So if t is used here and then y is written in terms of t, that means y equals, just replace this t with x's, and it's the formula. In other words, just giving you one more example, if this is x, if x is equal to t, and this here is y equals t cubed plus 4, this is essentially the graph of x cubed plus 4, y equals x cubed plus 4. This is a very common form of a path, and you want to be able to see this as the graph of y equals, and then this expression, except replacing the t with x's. The next example of a path is a line through a point x naught, y naught, z naught with the direction vector v. And the curve of the path is given by sigma of t is equal to x naught, y naught, z naught plus t times v, the vector v. We have seen this parameterization before when we talked about a line through a point in a direction v. Those are the two things you need to define a line. We had gone over that in chapter 1, and we'll just do a quick review of that right now. I have my example, but I did it in 2 dimensions because it's easier to draw. So here I have my point 2, 1, my x naught, y naught, and my direction vector is 1, 3. And I want to trace out a line that includes this point, but with the direction of. So something like this, except maybe a little straighter. If t equals 0, well, we're going to add 0 times v, which is 0, and then we're just going to add it to our vector. So we're going to get this point at the tip of our vector. Let's say t equals 1. So what we end up doing is we're going to add, if t equals 1 over here, we're going to add our x plus y plus our vector v. Graphically, that looks like I take my vector v, and then I'm going to move that vector to the head of my vector 2, 1, and then my next point is going to be this point here. So the 2 points I have so far are this point for t equals 0, this point for t equals 1. Now if I let t equals 1/2, for example, I would take half of the vector, half of the length of the vector, I would add it to the tip of my vector 2, 1, and I would get this point here for t equals 1/2. Now if I let t equals 2, I'm going to have twice the length of the vector. So when I move it up, I'm going to get this point out here at t equals 2. So you can see point by point, I'm getting this line here, which is more or less, starting at the point 2, 1, definitely starting at 2, 1, more or less parallel. If it's not parallel to v, it's because I'm not a good drawer. If I want to go back this way, I need to take negative values of t. But this is, again, this is how we would parameterize the curve of a line containing the point x naught, y naught, z naught in the direction of v. And t is our parameter that starts to draw the line out over time. Our next example is the unit circle in the plane is represented by the path sigma of t equals cosine of t sine of t. Often this is also parameterized as sigma of theta equals cosine of theta sine of theta, but t is fine as well. I made a chart of a few values of t and the cosine and sine of t. I would have put in more values, but actually I don't remember them. So this is what I can remember. So at t equals 0, cosine is equal to 1 and sine is equal to 0. So this is our point at t equals 0. As we come around at t equals pi over 4, we get square root of 2 over 2. So somewhere maybe around here. T equals pi over 4. When t equals pi over 2, we have the point 0, 1. That's a nice easy number. T equals pi over 2. And then when t equals pi, you noticed I jumped because I just dread doing all this. When t equals pi, we have negative 1, 1. So here we are at t equals pi. And at t equals 2 pi, we come back around to 1, 0. So we're coming over around here, and then we finally finish. And this is the direction of our curve. This last example I'm not really going to try to draw out for you as we go, but here's the drawing. And it's the function sigma of t is t minus sine of t and 1 minus cosine of t, and it describes the position of a function of a point on a rolling circle. So this is my circle, and it's rolling. So this is like at time t equals 1, and I put a dot on it so you can see, you can trace where the dot goes. As it rolls over on this plane, this dot moves to this position, and as it rolls over in time, it eventually gets to the top. And so if you trace out where the path of the dot, that's this blue line, that's this path here. So the circle lies on the xy plane and rolls along the x-axis at a constant speed. That is, the center of the circle is moving to the right along the line y equals 1 at a constant speed of radius 1 radian per unit time. The motion of the point, this red point, is more complicated. Its curve is known as a cycloid. So this is the cycloid curve. Next, we can talk about the velocity vector. Now we have established sigma as our path, which is our position at time t, so it makes sense that the velocity then would be the derivative of our position. So v of t, velocity, is equal to sigma prime of t, which is equal to x prime of t, y prime of t. In other words, component by component derivatives. Then the speed of the particle will be the length of the vector sigma prime of t, or in other words, s being speed of t is equal to the absolute value of sigma prime of t. Now we have the equation of a tangent line, and we did not parameterize by t since our sigma is parameterized by t, so we just chose another variable lambda. So our tangent line, we need a point that the line goes through as well as a direction. So the tangent line is going to be at sigma t naught plus lambda sigma prime of t naught. So this sigma prime gives us the direction of the tangent line. Our first example is sigma of t is equal to cosine t sine t t. Then the velocity vector is the derivative of sigma. So term by term, cosine, the derivative of cosine t is negative sine of t. In the y direction, the derivative of sine of t is cosine of t. And in the z direction, the derivative of t is equal to 1. So this is the velocity vector here. The speed, then, is the magnitude, which is simply sine squared, cosine squared, plus 1 squared, square rooted, which is equal to square root of 2. This path, by the way, is the one we had discussed before. It's this helix shape. You have the cosine t and sine of t, which trace out a circle, but this t in the z direction means that the circle keeps increasing. So it's kind of this sort of rising helix. And one more note, the point moves at a constant speed, square root of 2, but its velocity is not constant since it is constantly changing directions. Remember, velocity is not just a magnitude, but it's also direction. And since it's going in a circle, it's changing directions. Our next example is a particle moving on this same path here, sigma is equal to cosine t sine t, this helix, where t is time. And at time t equals pi, the particle leaves the path and flies off on a tangent. Find the location of the particle at time t equals 2 pi. Assume no forces act on it after it leaves the helix. So the first thing we need to do at time t equals pi, we need to figure out its location and also velocity, how fast and in what direction it's headed. So plugging in t equals pi into our sigma, we can find then its location. So we have cosine of pi, sine of pi, and pi, which is equal to -1, 0, and pi. Now to find how fast it's going and also in what direction, we'll look at the velocity, sigma prime of t. So the derivative of our sigma is derivative of cosine will be negative sine. Actually, we figured it out here. Negative sine of t, and then cosine t and 1. And then at pi, when it flies off, that will be equal to 0, -1, 1. So this gives us the direction of travel when it leaves the path and flies off on a tangent. And now, so we have a point and we have a direction. We can take a formula for the tangent line, which I denoted L of t. So our point at this, when the starting point for our tangent line is going to be -1, 0, pi. And then we're going to have plus t because I parameterized with t now. And then our velocity tells us the direction of our line. So that will be 0, -1, 1. Now I want to know the location of the particle at times t equals 2 pi. The thing is, I don't want to just plug in 2 pi here because pi is when it started on the tangent line. So I want to know where on the tangent line it is at 2 pi. That means it's only been traveling for pi units of time. So at t equals 2 pi, it has been pi units of time since flying off the tangent. So that's what I want to plug in on this tangent line. Before pi, it was going in the circle. And then at time t equals pi, it flew off. So this line starts at t equals pi. So if I want to find the time at 2 pi, I just need to plug in pi. And finally, our answer then will be L of pi, which is equal to -1, 0, pi, plus t is equal to pi, 0, -1, 1, which is equal to -1 pi, 2 pi. This is our final answer. Now that we've finished all the material for this video, we'll do a review, and then there'll be some problems for you to try. So first, we defined a path, which is a map from some scalar interval to Rn. And if sigma, our path, is differentiable, we say sigma is a differential path. The points sigma, sigma A and sigma B, that's the A from the endpoints of, and B, the endpoints of our interval. So sigma A and sigma B are endpoints of the path. And the image of sigma is called the curve of sigma. And it's useful to write t for the variable and think of sigma of t as tracing out a curve as t varies. We often think of t being time, and sigma t being the position of a moving particle at time t. And we can write sigma of t equals x of t, y of t, z of t when we're in R3. In other words, we can think of sigma t as a function of t that gives us the x-coordinate, the y-coordinate, and the z-coordinate. And we had 4 examples, 3 which I put on this review sheet. The line through the point, x naught, y naught, z naught, in the direction of vector v is the parametric equation of the line, which is the point, x naught, y naught, z naught, plus t, our parameter, times vector v. So again, it's the point, and v is the direction. We had another example, that's the unit circle in the plane, represented by the path sigma of t is equal to cosine t sine of t. And then last, we had the path t squared, and that was a curve that was a parabola. And you can see this is a parabola because this is the x-coordinate and this is the y-coordinate, and this tells us that y is equal to x squared. So it's essentially this parabola y equals x squared. Once we had sigma, and we think of that as denoting our position, sigma is the position, then it's logical to think of sigma prime as the velocity. So the velocity is given by sigma prime, and what we do is just go coordinate by coordinate, taking the derivative. Then once we have the velocity, we can calculate the speed, which is simply the magnitude of the velocity or the length of the velocity vector. Now we can also calculate a tangent line. So that to define a line, we need the starting point. So some position, we'll just say a position at t naught, and then the direction of the tangent line will be the derivative, also at t naught. And then we parameterize this line by lambda, our parameter lambda. We didn't use t since sigma is usually thought of as being parameterized by t. The examples we had then was another path, cosine t, sine t, t. This part here, cosine t, sine t, it's similar to this in that it's going to be a circle, but this t here in the z-coordinate means the circle is rising. So what you get is this helix. So then we can calculate the velocity by taking the derivative. So the derivative of cosine is negative sine, derivative of sine is cosine, derivative of t is 1. So this will be our velocity vector, and then the speed is just the magnitude, so that'll be sine squared, cosine squared plus 1, square rooted. And then another point is that the point moves at a constant speed, so in this case the speed is square root of 2, but its velocity is not constant, since the velocity isn't just a magnitude, but it's also a direction, and since it's circling, its direction is continuously changing. Our last example was to consider a particle moving on this path here, this helix, and at time t equals pi, the particle leaves the path and flies off on a tangent. So we start a line at time t equals pi. Find the location of the point of the particle at time t equals 2 pi. So first we wanted to define the line at time t equals pi. So we need a position and a direction. So the position is sigma of pi, which is cosine pi, sine pi, pi, which is negative 1, 0, pi. We need a direction, and this is on a tangent line, so we need the derivative of sigma. So derivative of sigma is negative sine cosine 1. We plug in pi at that time pi when it flies off, and we get 0, negative 1, 1. So this is the direction of our tangent line once it flies off. And it flies off at pi, and if at a time later at 2 pi, that means it's been flying on the tangent line for a unit of pi times. We plug that in at times t equals 2 pi into our equation of our tangent line, and we get that L of pi is equal to negative 1, negative pi, 2 pi, and this is our final answer. Next, I have two problems for you to try. The first one is to sketch the helix z of t is equal to a cosine t, a sine t, bt, and calculate its velocity. The second problem is if x of t is equal to 3t plus 2, t squared minus 7, t minus t squared, find the parametric equations for the line tangent to x at 5, negative 6, 0, which is equal to x1. If you plug in 1, you'll get this 5, negative 6, 0. Here are the solutions to the problems. And that is it for this video. Thank you for watching.